So welcome everyone. Thank you for attending tonight's program. My name is Matt Schumann. I am a programming librarian here at Carey. Before we begin, just a few things to note. If possible, please silence your cell phones as to not interrupt the program. This program is hybrid, so there are people attending via Zoom as well as all of you in person. I'd like to thank the generous donors to the Carey Library Foundation for helping make tonight's program possible. And I'd also like to acknowledge the late George Burnell for establishing our connection with tonight's speaker, as he brought her in previously for the Economics and Science series that he had run. Tonight's speaker is Dr. Kathryn Flanagan. She holds an astronomer emerita appointment at the Space Telescope Science Institute, where she has served as the James Webb Space Telescope mission head, deputy director, and interim director. The Institute is responsible for the science operations of the Hubble Space Telescope, as well as the mission and science operations of its successor, the James Webb Space Telescope. Dr. Flanagan came to the Institute in 2007 to head the mission office for James Webb Space Telescope, with responsibility for developing the acronym JWST Science and Operations Center. In her early career, she earned her PhD in physics at MIT, where she began working in the field of X-ray astronomy with a special interest in developing new instruments for space. She became part of the research staff at the Smithsonian Astrophysical Observatory and MIT, and she has worked on multiple flight instruments. She has participated in NASA's advisory structure, co-chairing strategic planning documents, and serving on advisory committees. She's also been active in astronomical community organizations and has been honored by election as a fellow of the American Association for the Advancement of Science. She's been active in education, beginning with service as a Peace Corps volunteer, teaching math and physics in the Democratic Republic of the Congo, and is a strong advocate for science outreach to the public in the next generation. So now, please welcome Dr. Kathryn Flanagan.
So this is a little bit of an experiment with the sound and the sight a bit, so just bear with us, we'll see what we can do. What you see in front of you, this ephemeral sort of image here in purple, a little bit brighter purple actually, is the Veil Nebula. It's the result of an explosion of a massive star about 8,000 years ago. So I actually did the homework to look up what happened 8,000 years ago. What else of note? Somebody sitting on a hillside would have gone, oh, look at that. This is a great millennium. But there were other things going on. They domesticated cats in that millennium. They grew barley from which you make beer, just saying. And proto-writing was developed. So all things considered, that 1,000 years was fantastic. But our century right now actually is pretty great. About 5 years ago, 7 years ago, there was the first detection of a gravitational wave. In fact, one of our colleagues in this area won a Nobel Prize for that, understandably. And I'd like to say the launch of James Webb less than a year ago on Christmas Day, I hope is going to actually contribute greatly to our scientific century. But anyway, this is a great century. It's a great time to be alive. And I just want to show you the first results and talk a little bit about it. So let's just set a context here. James Webb is a very, not only physically large observatory, it's an expensive observatory, and it's one that carries the hopes and dreams of astronomers all over the world. There are 3 great space agencies that actually contributed: NASA, the European Space Agency, and the Canadian Space Agency. By and large, when astronomers think of what they want, they're pretty much united all over the world about what they think would be wonderful. And with the cost and ambition of large observatories, they are now tending to be international, which isn't a great surprise. The results really belong to the whole world, and it takes the whole world to contribute. It was managed by NASA Goddard Space Flight Center in Greenbelt, Maryland. The prime contractor was Northrop Grumman, and my institution is Space Telescope. It's called Space Telescope Science Center, or STSCI, and we are in charge of actually commanding the mission as well as running the science operations. So we would host time allocation, peer review panels. We would help the outreach efforts. Whatever you've seen done for Hubble, we will do that for James Webb. But in addition, we will also orient the observatory, take the observations, do the actual commanding. Okay, there are two instruments in particular that I want to bring to your attention, but you need to understand that this is quite an interesting set of instruments that flies on this observatory. The whole thing is really a cut above what you would normally expect. In particular, we're going to examine closely why it has the shape and look that it has, why it was designed that way. We'll design that together. Why it has that crazy orbit. And we will understand why we want infrared sensitivity for this observatory. I'm going to point out two particular instruments. One is the NIRCam, the Near Infrared Camera from University of Arizona and Lockheed Martin. That takes the near infrared pictures that we will see and also provides spectroscopy. And the mid-infrared instrument, or MIRI, provided by the European Consortium and Jet Propulsion Laboratory. That'll take the mid-infrared pictures that you'll see. So I'll be showing you lots of images. Those two instruments are the one that did it. However, as my late husband used to say, spectroscopy puts the fizz in astrophysics. The spectroscopy that this observatory brings is really going to blow the lid off things. I don't have a lot of time to talk about it in this talk. If we do have time at the end, ask me about one example that I'll show you. But I have suppressed it from this just in the interest of time. However, this is a behemoth, a scientific behemoth. All right, we're going to design together this rather odd-looking observatory. I mean, if I had a full-scale model, it would go up in the atrium, a couple of stories high. The sun shield would be, a size of a tennis court. The optic itself unfolds and it's 21 feet across. What were they thinking, right? I mean, really. Okay, so let's design it and let's figure it out because we'll actually be able to see, yep, that was the right approach. Okay, up at the top here, there are four great themes, scientific endeavors that crystallize and focus the design of James Webb. The one we're going to be looking at to design it is this one. It's called First Light. What we wanted to do is to see the first galaxies that formed right after the Big Bang. So you got the Big Bang, then you got forming galaxies through gravity, and then as time goes by, they evolve. Galaxies have become, we know, beautiful because the ones near us are spiral galaxies, they have structure. We want to know, how did they get there? But it all starts with the very first galaxy. How did the first galaxies form? This one is my favorite. It's called First Light. It's the first light, first opportunity that you can see a galaxy. We know the universe is about 13.7 billion years old. So we want to see galaxies at 13.6 billion years old. We want to see them 100 million years or so after the Big Bang, maybe 300 million years, somewhere really close in there. So that's the goal. We're going to design to it. But if we can see galaxies that young at the beginning, as you will see, that means we're looking at galaxies very far away. If we can see those, we can see all those galaxies that are in between that have evolved more and more and more. And we can see the galaxies near us. So we can actually see how they change over time from early days until now. And that's called galaxy assembly. How do they evolve? How do they take their shape? What happens to them? There is one great reason infrared enters here, and that's because this involves what we call redshift. I'll explain what redshift is later. There's another great reason why infrared is good and why James Webb is perfect. And it has to do with the fact that infrared can see through dusty environments. Now, who cares about dusty environments? Well, here's the thing. All the things we actually care about are born in dusty environments. Stars are born in dusty environments. The planets that form around the stars are born in dusty environments. Our planet, you know, we actually are interested in seeing what happens here because it'll tell us something about what happened in our own environment. And the last one is, you know, we got a few great planets right around our own sun. That's our solar system. The best one being the one we're on. It does radiate in the infrared, but I'll tell you about that later. But here's the thing. Most stars have planets, it turns out. Something we didn't really know maybe 20 years ago. Most stars have planets. And a fraction of them are going to be in a really convenient, nice, temperate zone. That's pretty interesting. So a planet around another star is called an exoplanet. We're interested in exoplanets because you got to wonder, is it possible that life could actually exist on another planet? That's the great question that sort of looms ahead of us. And James Webb will take a stab at sort of going through all of this from the Big Bang to life. Covers an awful lot of ground with one observatory. So let's take a look. All right, you and I are going to design the first light machine. We're going to design what it takes to see the first galaxies. So I know that I want to see galaxies right after the Big Bang. That means the light has had to be emitted 13.6 billion years ago. And it's got to be in transit to me all this time for me to receive it today. So if that light has been in transit 13 billion years, it was emitted really far away from me, right? I mean, if it were at Mars, it would be minutes, but 13 billion years, we're talking major distances, the farthest possible reach of the universe. Okay, so the first thing I've learned by figuring it out scientifically is I'm going to see an object so far away that it's going to be faint. I better make a really big optic so that I can get enough light to detect it. Okay, we're good. First finding, big optic. Great. So what else do we need? Well, we know we're going to be looking at distant galaxies. One more thing, what does a galaxy look like? Well, it looks like this, right? And if you go out and, you know, maybe in Maine somewhere and look at the sky, can you see the Big Dipper? Yes. Can you see, you know, the Milky Way as a white haze? Yeah. So we know that galaxies are visible light, right? We can see it in some ultraviolet. So my question is, should I make my newly designed instrument detect visible light? Because galaxies are visible light. And the answer to that one is no, not so fast, Flanagan. So I'm looking at distant galaxies, and it turns out the whole universe is expanding, has been ever since the Big Bang. So my distant galaxy is emitting light here. And 13 billion years later, it's going to arrive at my telescope on Earth there. But in the meantime, the universe expanded. So what started out as ultraviolet invisible light got stretched, what we call redshifted. So it's no longer visible. Blues become red, become infrared. Under redshift, with long distances, visible light becomes infrared. So I'm going, okay. We're designing an instrument to see those galaxies far away. It's going to be a big mirror, and it's going to be infrared sensitive. Okay, we're just about there. Big mirror, infrared sensitivity. What could go wrong? But wait. Here's Fido, right? That's an actual infrared picture of a dog. In fact, if you look up in the Fountain of All Wisdom and Knowledge Wikipedia, what's the temperature of the Earth, you're going to find that the temperature is exactly in the area we want to look at, these little faint things. The Earth is a huge infrared emitter. Nice planet, but a real problem for us, right? And if the Earth is that bad, giving off a lot of infrared light, it's going to be a problem for us to detect those faint galaxies with that thing in the way. And then there's the sun. Nice star, no objection there, but I've got to do something about this unwanted light. I've got to have my mirror be in the shade from that. So I'm going to need something. I better put in a shield it from light. I better put in a sun shield or a parasol, you know? All right, so I got a sun shield, all right? We saw that little image earlier. The sun shield is big. The only problem is I got to guarantee that 100% of the time, the sun and the earth are always on the other side, so that my optic, my mirrors are always on the cold side, the sun and earth is always on the hot side, and the sun shield is in between. Problem with that is the earth goes around the sun. So if I want to guarantee that no matter where the earth is with respect to the sun, I better pick a special orbit, the kind of orbit that lines up the sun, the earth, and my telescope. If I can keep them all in the line 100% of the time, then I got a working operation here. Okay, that orbit exists and it's called L2, Lagrange point 2. Those are the 4 ingredients that give you this design. The sun shield, the big optic, the infrared detectors, and putting it 1,000,000 miles away at L2, farther than the moon by a factor of 2 more. I mean, it's far. And yes, it's cold, it's 40 degrees Kelvin. But apart from that, what could go wrong, right? So we designed this thing. This is an image of L2. I just wanted to show you what it looks like. There's the sun, there's the earth, there's James Webb in sort of a wobbly orbit, but it's always lined up so that it works just fine, that this sun shield can protect the mirror from getting the unwanted signal, the unwanted light. All right, so let's take a look. Here we are, 40 degrees Kelvin. What could go wrong, we say? You'll notice this whole thing was so large it had to be folded up, released in space, and then open up. Here is James Webb as it deploys. Here's the Earth, here's Hubble's orbit, here's the moon, and here's what's deploying as it's passing the moon. Took, I don't know if it's 30, I think it's 100 days to get to its final orbit. You're seeing the main mirror come up on the boom. This pink stuff is the sun shield. Hasn't been opened up yet, but now they're starting to open it slowly. I actually kind of thought they were crazy to attempt this. That was before I took the job. All right, so here's the sun shield, and you'll notice it's actually several membranes and not just one. And the reason for that is you don't want some rock, something puncturing one of them and making a direct hole that illuminates the mirror. So you put 5 of them. Now the big optic is coming out, the secondary is out, and there you have it. Our big mirror, our sun shield, our L2 orbit, our design is fine. I would like to mention that this is so large that the light pressure on it has to be compensated for. The light pressure on it does need compensation, and that's one of the reasons they put a trim tab there. So it was a complex and expensive experiment, but luckily it did work. Okay, so we know that infrared is ideal for redshift, right? We know that finding the first galaxies requires redshift. I just want to talk about that other great reason. Here's someone with his hand under a trash bag, and there's an infrared picture. You can see the hand clearly, how many fingers are extended, how far the shirt goes, because infrared can see through dusty, obscuring layers. Perfect. It's the perfect instrument to be seeing in some of these dusty environments that will be very interesting to us. So let's talk about those dusty environments. How do you make a star or a planet? Here's an area in visible light, which looks very murky and sort of clouded up. Something mysterious going on there. Here's the same region in infrared. All the stars that are there are now visible, as if we peeled back the layer. This is a star-forming region called Orion. This is to give you an example of the type of environment where stars are born. They require molecular clouds. You'll see sort of little tadpole structures here. That's a new star forming, and it's pushing a bubble out. And if we look carefully what's going on in there, here's the star forming, but you'll notice the disk and the dust surrounding it. Out of this stuff will come its planets. So star forming regions are really interesting to us because we will be able to look and see what's going on and what really happens at the birth if we get lucky. Okay, so how did our design work? Let's now look at what happened. It launched on Christmas Day, less than a year ago. On July 12th, the first science images were released. It took 6 months to get to L2, cool down everything to the right temperature, test it all, focus every single individual mirror so it works together, get all the instruments calibrated and good to go. July 12th was the big reveal date. That's the first time I got to see what was going on as well. So our question is, how did it work? And let's start with our Big Bang galaxies, right? How did our design come out? All right. First thing to remember is that this is an example, and it's a pencil in a glass of water. You know, and I know that the medium intervening between that object and our eye can sort of impact the image that is formed. We know it's a straight pencil, but it looks broken, right? So that's lensing. I'm going to call that lensing. This is refraction, because those of you who wear glasses know perfectly well that you can use that medium of plastic or glass to actually perfect your vision. And so it's not a big surprise that we should be able to do that, but we actually can do it with the universe. So we are interested in seeing very distant galaxies, really, really out there galaxies. And I'm going to take an example of, let's imagine I have a galaxy at the edge of the universe, you sitting there, and I have something in the way, a big cluster of galaxies in the way that is never going to be able to see. I'm never going to be able to see that thing. But what happens is galaxies emit light in all directions. However, some of this light, all directions, some of this light, if it comes close to the massive intervening, really massive intervening cluster of galaxies, will be bent. The light is bent by the curvature of space-time. And if you're lucky, it'll bend so that it comes and lands on your detector, in your James Webb. All right, so that's good. That means this little red light that I'm looking at is actually emitted by something way far away, and it got lensed by the intervening cluster. That would be great. So by symmetry, probably I would see this light maybe forming an arc, actually, or a circle, possibly. So let's take a look and see what we find. Here's the first image for our early universe picture. The color coding here, infrared is not, our eyes don't detect infrared, so we have to attach color. That makes sense. In this particular picture, the things that are red are actually distant. The things that are white are closer. So what we are looking for are arcs, red arcs. And as you can see, there are a lot of them. This white area here is that intervening cluster. And what we're seeing immediately in front of us are lensed galaxies way in the distance behind. And in fact, in this image, you can find some structure in those distant galaxies for star-forming regions, which is kind of hard to believe. I would like to point out that some of these orange galaxies that are distant candidates, they're kind of blobby. They don't necessarily look like spiral galaxies, and we'll have more to say about that later. But this first picture, immediately when you look at it, you go, aha, we got it. So our design only took us 15 minutes. I don't know why it took them 25 years. What was the big deal, right? Okay, so first light galaxies is the hot topic. And immediately, with that public data, people jumped on it. You could go ahead and analyze it. You can look, what did you find? Well, they were falling all over each other to publish. Here's a publication. Remember, the images were released July 12th. July 19th, 1 week later, here is a publication that says, I've reached redshift 13. I've just broken the bank on getting the earliest galaxies. And that was fantastic. But, fame is only his fleeting. Shortly after, on the 25th of July, a week later, less than a week later, someone comes up with redshift 16. The publication rate was so crazy that people were scooping each other by, get this, 13 seconds. 13 seconds. And they were laughing because it was so ridiculous. But here's the thing. It kept going on and on and on until I looked in September. The September Scientific American had this headline: JWST's first glimpses of early galaxies could break cosmology. You have to laugh. I'm looking at this because I'm getting ready to give a talk, and I've been out of touch for 2 months. I'm going, oh, really? Turns out there were so many galaxies that they were detecting from the early universe that we designed it to find one, right? They were detecting so many that it looks like it was a problem, like maybe more than you would have predicted. And so I actually literally got in touch with the current mission head who's running it, and who is also a cosmology expert in this area. And I said, so is there a problem? And he goes, well, there was imperfect calibration, but it's excellent now. They're checking spectroscopically, another technique to see if the detections are right. He says, I think the doom of cosmology is greatly, exaggerated. Just hang tight and we'll see what happens. So he said, don't worry just yet. But it is kind of an interesting problem. And I noticed Scientific American came out with another article because they're still worried. So anyway, this one area of all of our themes is an outrageous success so far. Things are always great when they go the way you expect them. And for scientists, it's even better when they don't. All right, now let's talk about those dusty regions, star-forming regions. They are spectacular, visually, when you see what happens. I want to show you my laptop because the image is a little bit better. This is a little washed out right now, but you can see the links later. This dusty region is another famous star-forming region. What's happening here is there are some big, bright stars up above the screen that you don't see, and the particles and radiation from them are pressing down on the matter and making this strict edge, okay? And what's interesting, you see fingers of material, you see yellow orbs showing up. These are all interesting structures because within them is probably beginning stars to form. This particular one is called Carina, but it's not the only one we're going to look at. Let's try this now. It's a movie.
NASA's James Webb Space Telescope has snapped this view of the pillars of creation in mid-infrared light, showing us a new view of a familiar landscape. Thousands of stars have formed in this region. This is made clear when examining Webb's recent near-infrared image. But in mid-infrared light, the majority of these stars appear to be missing. The pillars are flush with gas and dust. While mid-infrared light specializes in detailing where dust is, the stars aren't bright enough at these wavelengths to appear. Instead, mid-infrared light excels at observing gas and dust, like young stars, that still have their dusty cloaks. These are the crimson orbs toward the fringes of the pillars. In contrast, the blue stars that dot the scene are aging, which means they have already shed most of their layers of gas and dust. How vast is this landscape? This bright red star and its dusty shroud are larger than the size of our entire solar system.
So in this case, invisible light, this would be sheets of material standing in your, obscuring your vision. In the near infrared, you could see the stars show up, right? In the mid-infrared, something interesting happens. The stars are not at the right temperature and they're not bright enough to peer through in the mid-infrared. But the other thing about the mid-infrared that I actually love is that that dust starts to glow. And so in that picture that you saw earlier, you saw a red background. That was the glowing mid-infrared dust. So all of these different wave bands give you different information. Sometimes you can see the dust, right? So it's pretty good. Here's one. Can we get, oh, it just disappeared. We're good. Sorry. Right above this star, you're going to see a bubble. Do you see the bubble here? Okay. In an animation earlier, I showed you something tadpole-like structure, which was a new star forming. That was interesting to astronomers because they thought maybe there's a new star forming there or a brand new one that's pushing out the bubble around it. They liked the idea of that because this nebula, the Tarantula Nebula, is chemically very similar to the universe when it was really forming in a star forming time period several billion years ago. And they think if we can examine this, maybe we will understand better what was happening then. That's farther away, it's harder to detect. But this is chemically very similar. So they were interested in seeing what would happen in Tarantula. So they looked at this bubble and they said, oh, maybe there's already a new star. Too bad we didn't catch it right at the birth. This is where spectroscopy came in. They did a spectroscopic analysis of the chemicals in that, and they figured out it's not born yet. They have caught it at the birth. Fantastic, right? Just a fantastic opportunity. All right, next one, she says. Okay, yes. The last one I want to give you is the Southern Ring Nebula. I just want to talk, this is what happens when a star dies. Sometimes it sort of goes through pulses and it emits some material into the surround, and that material expands. What's going on here is a near-cam image, near-infrared, and a mid-infrared image, near. I want you to see if you can see the difference. On this image, there are two stars at the center, which is not obvious in the near-infrared. By looking in the mid-infrared, we discovered that, in fact, it's a binary. And of course, it's emitting these rings and rings as it evolves towards death. Okay, now, this is not my specialty. It's really local for me, but we're going to talk about the solar system because I find that pretty interesting. James Webb has already looked at 3 planets. Pretty good. I'm going to talk just about one, and maybe later I'll show you a picture of the other, but I encourage you to go ahead and look and see what they've done. Okay, the ones that they've seen are Mars, Neptune, and Jupiter, okay? Now, observing planets in the solar system is tricky because they actually move. You'd think that's not a big problem, but in fact, you have to make Webb capable of following the object as it moves. If it were stationary and the object moved, you'd get blur. This is not helpful. You need to be able to track it. So moving target tracking was one of the implementations that we had to do after I got there. And it's able to look at anything from Mars on out. So that's really good. So let's take a look at one of these. Neptune, that was the far one out there. So it's going to be really cold. Well, I actually looked up the Hubble image of Neptune. And Neptune is a little bit blue. It's kind of blue in the Hubble image, invisible light, real blue. And the reason for that is there's methane in the atmosphere. Turns out that methane absorbs light in the infrared. And so Neptune is actually pretty dark. And the reason it's dark is because of the methane in the atmosphere. If the light from the sun goes into the atmosphere and goes all the way through it, it gets absorbed and you don't see anything very bright. There are regions, however, that are bright. And those regions are caused by clouds. The cloud in the atmosphere reflecting the light of the sun before it gets absorbed. And so what we're seeing in front of us are some clouds, right? And you also will see, if you look carefully, there are actually 4 rings here. The 2 fainter rings that are a little hard to see right now, those 2 fainter rings were detected, this is the first time they've been detected in infrared, is with James Webb. So it's pretty nice. There's one other thing here, a small faint band around the equator. Neptune is known to have winds, and it turns out that the perception is possibly the atmosphere comes down at the equator, warms up, and that's why you see a little band. Now let's step back a little and see what the big picture looks like. There's Neptune. It has 14 moons, of which this image caught 7 of them. And it has Triton out here. Triton is massively bright. what's going on with Triton? First of all, Triton is very different. It doesn't go along with the rotation of the planet. It goes backwards, okay? Retrograde. And the second thing about it is it's so bright. And why is it bright? We know that this planet is dark because of the methane. Turns out the surface of Triton is a frozen sheet of nitrogen, and it reflects 70% of the light that lands on it from the sun. That's why it's sort of burning out your detectors here. Pretty good, not bad. All right, now let's see what happens when we talk about galaxies. We saw a picture of a red galaxy that somebody published, Z = 13. It was a red blob. So those old galaxies look like red blobs, right? Well, maybe, yeah, they do. And we know the galaxies around us look wonderful and spiral, and they have structure. To get from blob to spiral, what goes on? Let's take a look. This is the Hubble Ultra Deep Field, looking deeper and deeper and deeper backwards in time. And they're taking several candidates to show you what do the galaxies look like as you go farther and farther away and closer towards the Big Bang. Okay, close to the Big Bang, red blob. 10 billion years ago, kind of spotty. 7 billion years ago, starting to look very nice. 5 billion years ago, beautiful structure. So something happens to our galaxies is they start looking sort of like something in a kitty litter box, and they wind up looking like this. Something in between happens. That's the evolution of galaxies. What do you suppose is causing it? Well, these are lovely galaxies in various images from great observatories as they've been seen, and they have structure. How did they get the structure? Here are simulations of actual things that are seen on the sky, actual final shapes, an imagination of how they may have come about. So for example, a collision of two galaxies form that shape, which is a Hubble image. A few others are going to show here. See, the simulation does a pretty good job of approximating what we're actually seeing on the sky. And if you think about the early universe, you know it's been expanding. But back in the day, it must have been pretty crowded. All those galaxies close to each other, maybe interacting with each other, right? And so we see here that interactions do affect the shape of galaxies. Maybe when they were close, they impacted each other, changed each other's shape, and eventually over time wound up like this. It's a good hypothesis. So let's take a look. This is the first light image for Stephan's quintet. It's a series of galaxies, and I just want to point out, you can see structure. They are actually impacting each other, and their gravity is causing streamers to form and effects to happen. And so this is a living example of how galaxies that are close enough together interact and change each other's shape. All right, now I don't know where we're going. Let's find out. This was going to be my hidden slide.
How do we learn about a planet's atmosphere?
Okay, this is the stuff that's sophisticated. I was going to surprise.
How do we know what's in the atmosphere of an exoplanet? The majority of known exoplanets have been discovered because they partially block the light of their host star. This is called a transit. During a transit, some of the star's light travels through the planet's atmosphere and gets absorbed. The light that survives carries information about the planet across light years of space where it reaches our telescopes. However, the planet is very small relative to the star, so it is still very difficult to detect, which is why we need a big telescope to be sure to capture this tiny bit of light. So how do we use a telescope to read transit light? Stars emit light at many wavelengths. Like a prism makes a rainbow, we can separate light into its separate wavelengths. This is called a spectrum. Visible light appears to our eyes as the colors of the rainbow, but beyond visible light, there are many wavelengths we cannot see. Now back to the transiting planet. As light is traveling through the planet's atmosphere, some wavelengths get absorbed. Which wavelengths get absorbed depends on which molecules are in the planet's atmosphere. For example, carbon monoxide molecules will capture different wavelengths than water vapor molecules. So when we look at that planet in front of the star, some of the wavelengths of the starlight will be missing, depending on which molecules are in the atmosphere of the planet. Learning about the atmospheres of other worlds is how we identify those that could potentially support life, bringing us another step closer to answering one of humanity's oldest questions. Are we alone?
Okay, I've suppressed, I have something to follow up here. I'm going to leave it until the end of the talk to see if we have time, but it's very possible one of the students in this room could make a discovery with this data, okay? We'll finish this and then we'll go back to it if you want to. Does that sound like a plan? Okay. So now let's talk about the kinds of things that you can do. Much of this data is already public. So I just wanted to show you some examples from what we call citizen scientists. Amateur astronomers, they're not professionally trained, but they do go take the data and they go and they look and they filter it with images. They do exactly the type of thing that we would do at Space Telescope to bring out the features. This is the Phantom Galaxy right here on the upper left. The lower right is NGC 7496. I'm accrediting Judy Schmidt, who did the image processing and made this public within a few days. And I went online and I found, I think at the Space Telescope archive, I found the Hubble images because I wanted to compare how it looks in visible light next to the infrared. And here's the Hubble image. Very similar, but as you can see, a little bit more fuzzy in certain ways. Different features show up. She did Jupiter. Can you believe this didn't come from a NASA release? This is Judy Schmidt working with one of the astronomers on taking the JWST data for Jupiter and publishing it. It's spectacular. Now, you already have the training. You're seeing white here and white here. And what you know that probably means clouds. And in this case, over the great red spot, haze, reflecting back the sunlight. So you're already diagnosing what it is you've seen. And in order to do this, she was very sophisticated. Jupiter moves. And also you have to, each image, you have to stack them. Maybe Jupiter rotates. You've got to make sure that the red spot isn't rotating image to image. You're going to have to fix what you actually stack together before the final image. And she had to do that. Kudos to her. I actually went online a few days ago to see what else we could do. Hanukkah's coming, Christmas is coming, holidays, New Year's. You can actually download templates, these actual forms, and print them out at Staples or wherever you like. So I'm actually thinking of doing that with my favorite JWST image. And finally, I just wanted to put, for anyone that was interested, where to go if you want to get the data. Where do you go if you want to see a podcast on how to analyze and make an image? Where to go if any of these things, right? And I can leave that up afterwards if you like. And finally, I want to thank Matthew, the current mission head, Massimo Stiavelli, who did give me my midnight response to, to my cosmology questions, Office of Public Outreach and the Carey Library Foundation. And I'd like to finally thank George Burnell, who sort of got me into giving some talks at the Carey Library, and he passed away before we could actually get the results, but we're thinking of him, so thank you. So shall I?
So we can take questions, and then we'll also have some questions on Zoom.
Okay.
We can pass around a mic, and then also we'll alternate back and forth.
And Matthew, can you unskip those 3 slides when we do that? Because people will probably want to see.
So thank you very much for the terrific talk. I came to wanted to find out what was distinctive about the Webb telescope, and you covered that very well, so thank you.
Thank you.
My questions come from huge naivete astronomy, so forgive me. You said that the earliest stars are 13 plus billion light years away. Why are they all the way away? Why aren't we in the middle and they're less than 13 billion?
So the way I view this, and I'm not a cosmologist, I'm too dumb for that, but the way I view this is imagine a balloon, okay? And you put dots on the balloon, one for each galaxy. That's about just after the Big Bang. Then you blow up the balloon, okay? So all of the galaxies, all of the dots are moving away from each other. No one galaxy has a preference over the other. No one is at the center. But if I'm on one galaxy and I'm seeing all the galaxies around me moving away, I'm figuring I'm the center, right? The center of the balloon may be the center. So they are moving away. They are very distant because that's the state of the balloon now, right? So if I want to see light from a galaxy right after the Big Bang, that light has to have been emitted nearly more than 13 billion years ago. The only way I know to guarantee it's light that was emitted that long ago is to look at a galaxy 13 billion light years away. That's the only way I can be sure that that light is when it was young. Because guess what? Here's the bad news. That galaxy probably looks like we do. Probably spiraled by now. I need the light from when it was young. And that's good. Yeah.
So we have a question from Zoom. Someone said that there's a hypothesis that dark matter is consisted of dark photons. So can the JWST detect dark matter?
No, not in the way that suddenly it illuminates. Most of the way that I understand that astronomers detect dark matter in the traditional, with traditional telescopes is by the impact it has, right? If, for example, you see the cluster of galaxies that lenses distant objects, let's imagine you didn't see something very bright there. You saw lensed galaxies. You'd have to conclude there's something very massive there causing space-time to bend. So what you do is you look at sort of the impacts to imply where it is, but telescopes normally don't detect it directly. And that, they detect the results. That's not unusual. Our way of experimenting on the universe is very passive. We receive the light and we figure it out. We can't actually tweak it. Right?
Hello, thank you. I was curious about the fact that this bubble's expanding. It's like embers of a fire that go off into the night, right? Does that mean we will eventually freeze over time as energy is lost and the bubble expands into an ice cold fire end?
The alpha and the omega, right?
Yeah.
The truth is, I don't know, because the more we learn, the less we understand. So for example, I'll give you an example, right? With gravity, if I throw my keys up, it'll slow down and then it'll fall back. If I throw it up really, really, really fast, maybe I can put my keys in orbit. But our understanding of gravity is such that we would not expect something that was self-gravitating, all that matter that was attracting itself. We don't expect it to start speeding up. That is not normal. And that is dark energy. They got a Nobel Prize for figuring that one out a few years ago.
That's my next question. That the structure of the universe could be the hidden energy, actually is the dark matter that makes up the fabric of the between the stars.
It's likely that, I'm way out of my depth, but it is likely that dark matter was influential in forming up the first galaxies. So some of the structure of the universe probably has a lot to thank dark matter for, but I've already told you more than I understand.
On the exoplanets, have we actually discovered any carbon atoms in the atmosphere?
Okay, I'm going to unskip the slides now. Okay, because this is a great lead-in, and I need a student in the audience, somebody who's going to have to remind me of something. Do you want to help me? Okay, what's your name? Evelyn? Okay, Evelyn's going to help me remember something. It was, this. That was a great question. Okay, so you just saw a movie, and what the movie told you is that when light shines through when a planet goes around a star, the light shines through its atmosphere. And if the planet goes in front of it, you might be able to detect a little, it's blocking out the light while it's in front. And then when it goes around behind, the light is full. So you might detect that the light changes. But the interesting thing is spectroscopically, is when the light goes through the atmosphere, if the atmosphere has oxygen, it'll absorb an oxygen line. If the atmosphere has carbon dioxide, it'll absorb the carbon dioxide line, right? So you can detect maybe what's going on in that exoplanet. That's what that movie showed us. Now, why do we care about that spectrum? This is actually a spectrum of the Earth's atmosphere, the light coming through the Earth's atmosphere. It's called Earthshine, and it has several little absorption features that are indicative of our planet. And it goes from optical light to visible light to infrared. So for example, there's signatures of oxygen. Good for us, we breathe it, right? There's signatures of water vapor. We know we have water and clouds in our atmosphere, so the signatures show up there. We have signatures of methane, which, cows produce, and carbon dioxide, which we breathe out and which volcanoes produce. And here's one big absorption feature. So Evelyn, I'm going to ask you to remember one thing, because I always forget it. 4.3 microns is the absorption for carbon dioxide. Carbon dioxide, okay? 4.3 microns. Let's take a look at one of the exoplanet observations that Webb did, one of the 4 great observations. Okay, detecting a transit. Detecting a transit is normally really hard. You sort of see a little dip and you go, yeah, I think it's there. Here you are. Here is the transit of a planet that is not in front of its star and then goes in front of the star and causes a dip and then passes beyond. So the dip is so clear you can see it from the back of the room. That's a transiting exoplanet, no problem. So they looked at this transiting exoplanet, which I think is WASP 39b. It's not written here. Yeah, WASP 39b. They looked at it with 3 filters because they wanted to see if it was different in the various filters, meaning they looked at it in 3 microns, which is the blue dots. They looked at it at 4.3 microns, which is Evelyn's, 4.3 microns is what Evelyn's going to help me with. That's carbon dioxide. And they looked at it at 4.7 in the red, okay? The red dots or the red triangles or squares or whatever, 4.7. So when the exoplanet is outside, I see red, I see green, and I see blue, and they all look mingled up here. They all look mingled up here. And at the bottom, when the light is going through the planet, is right here. So that's blown up a little because I think I see something. They've blown up this region, and Evelyn, I'm going to ask you, do you agree with me that the green squares are lower than the other 2 colors? Yeah, right? And the green squares, 4.3 microns, that's carbon dioxide, right? So carbon dioxide got absorbed more than anything else. That means that atmosphere probably contains carbon dioxide. So let's go and take a look. Bingo, there it is. By eye, we could see it, but in fact, it's the first clear detection of carbon dioxide in an exoplanet atmosphere ever. And we were able to see it right here in the back of the room. Not bad, coming out of the box. Okay, so that's it. Those are the slides I wanted to show. Are there more questions?
We do have another question on Zoom, just kind of repeating the dark matter question, but how can scientists be sure that the light seen as bending in some of the JWST images are not being bent by some other cause, like dark matter or otherwise?
Dark matter may be part of the ingredient within the clusters. There are some X-ray experts over there who probably know a lot more about it than I do. But yes, it's probably contained in some of that heavy mass.
When we looked at the image that was 13.6 billion light years away, that light was emitted 13.6 billion years ago. And how far away is that galaxy from us now?
Oh boy, that's a good question. The answer is farther, I think. And in fact, I'm being very relaxed about how I'm representing this, but there are other astronomers who actually do that math. I'm just giving it to you representationally, but yeah.
And is there a difference at those kinds of distances and with the universe expanding, how much it's going away from us is because of the momentum from the Big Bang forcing a movement versus the expansion of the universe also making it further away?
I think I sort of am thinking of those things as the same, but I don't know if I'm right. I'm not for sure. I'm for sure not a theorist. Any other questions? I'm happy to talk to people separately too afterwards.
Thank you. Going back to the telescope observatory itself, you showed that amazing movie of its gradual unfolding. Were you able to test any of that on the ground? And how do you know it's going to work? And what kind of engineering preparation goes into that?
So much. So I have a motto, experience is recognizing a mistake when you make it again, right? So yes, a lot of testing went on the ground. That's why Webb took so long. You have to practice unfolding the sun shield. And that's when you find out, oh, that you can't do that, that tears it. Or you have to practice raising up the boom. You have to practice unfolding the mirrors. The hard thing, you also have to practice how are you going to focus these mirrors? Because when you unfold it in space, you got all these hexagonal mirrors looking out in your directions. You had to go through a process that gets them to a common focus. So all those things have not only to be thought through, but in most cases, testing on the ground, either with us, usually with a pathfinder first, and then later with the real thing. All those things happen. One of the things you might be interested in is, the Apollo test chamber was this massive, vacuum chamber, and it used to be on the tourist circuit to go see it. It was like the only chamber big enough to test James Webb. So they took it off the tourist circuit, cleaned it out, and they used that to test the mirrors. And there's a picture of mirrors going in with this huge NASA door open. So it's kind of interesting that we're repurposing these things from back then. Any other questions? Evelyn?
I have 2 questions.
Sure.
What's a light year?
What's a light year? Okay. A light year, sorry, that's a buzzword. A light year is the distance that light travels if you give it a year to keep traveling. So, for example, if your car is going 30 miles an hour, an hour it would go 30 miles. Light goes so fast, we just call it light years. How far does it go in a year? That's what light year is.
Why was the telescope called
James Webb, it was named after James Webb. He's not a scientist, so it's unusual to name an astrophysics mission after someone who's not a scientist. However, he was an early administrator of NASA who, in my opinion, put the science in NASA. He decided that NASA wasn't just going to be, a manned space type of operation, but it was also going to involve industry, and it was going to involve universities, and it was going to do science. And because of that, we honored him with that name. Because NASA has many great parts to it, but the scientific component really is one really outstanding part, and it might not have happened if it hadn't been for him. Okay, then I think, should this be the last question, do you think? Okay.
Yeah, I just wanted to ask kind of a personal question is, this must be the pinnacle of your career. and what happens next for you?
Oh, thank you. I really appreciate that. And I'd like to acknowledge that mission, as all great observatories, all great missions, I know people that have worked for decades on Chandra, for example, is a sacrifice not just for the individuals involved, but for their families. They also serve who only stand and wait. There are all these vacations missed and these late nights and suppers and all these events that don't happen. Everybody supports the effort. And a lot went into James Webb in the same sense. Some people, like my husband, didn't live long enough to see the launch, but they contributed to this. So I want to acknowledge them before we go farther. In my case, I've retired, and I have this saying: wise men plant trees in whose shade they will never sit. The name of the game now is to enable the next generation to carry forward with whatever their great dreams are. There is a path forward and a plan forward in astronomy already, for astronomy and astrophysics, and where do we want to go next, and what are we going to see next? And believe me, when you make the dream, it's almost guaranteed you don't know how to get there yet. In the case of James Webb, it took 10 new technologies before they could build it, right? It's going to be the same for any of those great endeavors. And I actually would like to say, I think it's important because I discovered that when the first images were released in July, there was a metric, a news metric that they count to see how much impact it had. And it basically told me that there was the opportunity for every person on the Earth to have accessed those images multiple times based on that metric, which said to me, this is not about scientists. This is about people, right? And what people dream, what they think about, what they aspire for, what sacrifices they're willing to make, and how much it matters. The fact that it's international is not a surprise. The fact that regular people, are going and trying the data and making images and showing us Jupiter, right, isn't a surprise, because great things are done by those types of dreams. And I actually think, scientifically, of course, we're going to continue to dream, but I think it's actually a statement about what we can do for any kind of big project of any sort or any great endeavor. So my commitment is planting the tree under which other people will sit, right? So it's the next generation writ large is where I think I want to go.
Well, thank you everyone for coming, and thank you so much for sharing your expertise and all these beautiful images. Thank you.
Thank you so much.
Thanks for bailing me out.
Oh,